3D 哦，那就
通常是比较麻烦。
对，那就
通常是比较麻烦。
对，那边
还是要转一个地方。
但是这个焦点对爆炸很麻烦。
它那是焦点，
所有人都打太大麻烦，
叫北大跟清华是焦点。
对，
清华他们这个清华他反正是不管，就是你是 up to 多少
啊，
就是在那个一个线之内，
这样子比较好。
对，你要给你
比较 flexible，
哪怕你定低一点也行，你其他的都不管你。
对，是。
哦，那是什么？是真的吗？
它是 certain up to 这个是，就在你少于这个，但你就是他不管你从哪里来，
就是你的绩效大，对不对？
最后你是过了。当然就是像你说，如果你到别的地方，你还是要签一个这种伞，对不对？
对对对。
就是说，你要从别的地方的话，有这个你要访问两个地方和那个地方的。这个挂上就可以是吧？
对，
不用打开，不打开。
对，我帮你打开。
先打开。OK， 那是不是到里面了？差不多还有1分钟啊，
可能慢一点点。
哦，慢一点点，好啊，好。
台北市某地方下大雨。
啊？
某地方
下大雨，Okay. All right. So we'll continue. So maybe I'd like to make a remark first, because one point I want to about the Hitchin-Thorpe, in the sense so yesterday we talked about possible Hitchin-Thorpe inequality for the Ricci shrinkers. So notice that we don't have, of course, it's a topological quantity. So suppose M4 G is compact remaining. And let chi of M to be the Euler number, tau of M to be the signature of M4. Then we have the following: the 2 chi plus or minus 3 tau is equal to the integral, which is 1 over 8 pi squared. Then in this case is going to be equal to the integral of M4 for W plus or minus right at squared minus traceless of Ricci squared and plus scalar curvature squared over 12 and integrate. So this is for a compact or for Riemannian manifold. So in this case, yesterday I wrote down the relations So in the sense, if say now M4G is a compact, so compact the Ricci shrinker, we could use any metric related to G, right? So typically we could use any metric, say, in the conformal class. So not necessarily have, so it's a question, what is the metric we try to pick? This is for any, right? So certainly, we can try the soliton metric, but you could also do other maybe most likely conformal metrics to work on it, right? So we could use any conformal metric, not just G itself. Okay, so that's a remark because that's why we haven't found maybe the right metric to plug in yet. So people have been tried to some degree. So we have to be a little bit open-minded. They try and find out. Yes.
I think there are some people they sit there looking at some regular solenoid. Before that, you have long time small solenoid.
Oh yeah.
And then they can.
That's of course you assume. If that's already essentially put some restrictions on because you have like Fu Chuan, I think is in the sense. Yeah. So I'm talking about the general. I didn't mention any partial sort of results towards that. There's some partial results towards that assume certain conditions. Then it could be true, but we are interested in more.
I think they derive some inequality.
That's right. Using the long time existence, you could, because long time existence then actually are improving metrics and then you can work with it. Yes. So maybe later on I can list some of the partial results. You could search for some. There's a few results. Yeah. But I think we are really aiming at the general ones without further any assumptions. Yeah. Okay. So that's just a remark about this. All right. So let me move on. So today I'd like to start talking about another aspect, explore another aspect, that means variational structures. For mean curvature flow, that has been very successful. And for example, generic singularity due to coding Minkowski, and I think we're going to hear Jacob talk about more along those directions possibly. In the mini course and his talks. So I want to say today we're going to discuss in the Ricci soliton case. So here I'll be talking about the variational structure. So today I'll talk about generic type 1 singularities. Of the Ricci flow. That is, we're going to talk about, say, entropy, Paramant's mu entropy, stable Ricci shrinkers. So that is about this one. So we're going to explore the variational structures. So let's start with some basic backgrounds. So, all right. So let's start with the well-known Hilbert action. And so here we look at for any compact remaining, say M, N, and G, this Einstein-Hilbert functional, Einstein-Hilbert functional is, of course, we know is the total scalar curvature. EG is equal to scalar curvature of G and d mu G. Right, so here RG is equal to the scalar curvature of G. Now, are the graduate students a bit familiar? I probably may mention just some of the variations in this case because that will be this. Then the first critical point is Ricci flat matrix. Okay. Yeah. So it's well known that if we look at the first, so let H to be equal to delta of G equal to the first variation of a metric G of T, say. Right? You have family of metric the variations, so in a sense of G. Then we have the fact that the Ricci curvature, the first variation of Ricci curvature is well known. In the sense, I'm going to just write it here. That's going to be equal to, you can write down by direct computations, this is the equal to J, and so I'm going to write the I and the K. So this is I, R, and JK plus it's symmetric, so you got the J covariant derivatives, and here is K and IJ, sorry. And then you have two more terms. Sorry, that's the H. Yeah, and you have the Laplace of the variation H, and then you have the Hessian of the trace of the H. So this is by just direct computations, right? So if you, in the sense, this is not the optimal one, that, for example, you can simplify it into the following, which is called some parts will be the divergence of the variation, and this is not quite yet, so you like to switch the derivatives, and if you switch derivatives, you get divergence of the H, etc. Okay, and if you do that, so what you're going to do is you get the say 1/2 of the basically the part of Ricci-Novich, so which is Laplace of, I'm going to skip the indices, let me just write down, and then you have the minus twice of the curvature acting on it, so you have IJKL, and here you have HJL, and then you have the Ricci acting on it, so it's IJHJK plus the other way around, so HIJRJK, and this is essentially part of Ricci-Novich operator, and then you have the divergence part, but actually, let me write it down. So you have the divergence one, so DJDIHIK plus that's the get this part. So critical points, as it well known, of EG are precisely Ricci of G minus R G over 2G is going to be equal to 0, or Ricci is if n is bigger than or equal to 3, right? And we know that one. And then so if we add EG and then the constraint with the volume constraint normalization, that the volume of mg is identically equal to 1, right? So equal to d mu of g is equal to 1, then we get the Lagrange multipler, right? So then this implies can I erase this? No. Anyway, the Einstein metrics are all the critical points. Critical points are Ricci of G is equal to the constant rho of G. So with the constraint, right? So that's Einstein metrics are critical points of the Hilbert action with the volume constraint. Now the similar picture was found by the variational structure was found by Perelman. So that gives us another tool to analyze the shrinking solitons and also monotonicity for Ricci flows. So let's quickly recall that, and then we'll talk about the second variations. Now, so here is the f, so functional, well-known f functional is, so if we have m and g, and for any f smooth functions, so here just the general remaining manifold, right? Consider the f functional is, you have a metric G, and f is simply the scalar curvature gradient f squared. That's well known, e to the minus f and d mu g, right? Okay, we know. So now in Perelman, so this appears in string theory. So in Perelman is looking at this sort of lambda entropy. Of the G and F subject to the weighted volume constraint to be equal to 1. And F are smooth functions, right? Yeah, so it's sort of similar to that. And this has a physical interpretation in string theory, but this is purely geometric. Now, so here is the f, so functional, well-known f functional is, so if we have m and g, and for any is achieved in the sense is achieved by some f. So we're going to say by some f. So in the sense that this is going to be equal to f, maybe. And second is the first variation precisely leads to the steady solitons. The second variation, or first variation of lambda g in the direction of h is going to be equal to, actually in this case is Ricci plus Hessian of f star and h e to the minus f star. So critical points are steady solitons. All right, so this is the one that Paraman found rather quickly afterwards. Next one took him much longer time according to himself, right, at the time. So that's the one, the W function. And new entropy. I think this is one close to the shrinker. The volume entropies in curvature flow. All right. So in this case, for any metric G, for any F, and for any positive constant tau, tau times the scalar curvature plus gradient f squared plus f minus, let's see, it's the plus f minus, and I think for simple, yeah. But let me just double check the, yeah, that's correct. So plus f minus n is just normalizing constant. In the sense, and then you got the 4 pi tau, so the minus n over 2, so the backward hit kernel type weight functions e to the minus f and d mu g over the m. There's two. Thank you. That's right. Scaling factors. So you got tau. And of course, you can do two-stage sort of minimizing process. Minimize just over tau, and then so. But if you minimize, so just depends on the h. So this is the mu entropy, then it's going to be essentially the 4 pi tau to the minus n over 2 e to the minus f d mu g. I guess I didn't really one. So here you minimize F and tau. And again, it's going to be achieved. So this actually is easier to see eigenvalue problem, and this is slightly nonlinear log Sobolev type of best constant. So you probably have seen it. Okay. Yeah. And the first variation, so what Perelman found is the variation of matrix G is H, and then the of this one is going. Yeah. Let me get the constants right. So essentially, is to define the shrinking entropies. So yeah, so that's the 4 pi tau, and you got the Ricci. Yeah, tau times Ricci plus the Hessian of some F star, similarly achieved, and you got the tau star, which is achieved, and then minus the 1/2 of the metric G, and all these, you got inner product with the arbitrary first variation, and you get 4 pi tau star to the minus n over 2 e to the minus f star d mu g. Okay. So the critical points will be the essentially give us the shrinker. Ricci shrinkers, gradient Ricci shrinkers. So critical points are simply Ricci plus some potential function f is equal to 1 over 2 tau star of metric G, and that's exactly gradient Ricci. All right. Yeah. So, okay. So one of the, as we mentioned in the compact case, I'll discuss a little bit later. There are some classification results exploring the conformal sort of structures. For example, Weyl curvature equal to 0, divergence, harmonic Weyl, and Bach, etc. But those are still rather special sort of curvature restrictions. And so for study Ricci flow, once it's dimension 4 or more, I think it is pretty difficult to try to classify sort of all such shrinking solitons. Well, for 4 dimension in the non-compact case, we have more hope. You will hear from Kochwa's talks and Ovidio Montiano's talk. But for compact ones, even harder. We don't know even classify Einstein ones, 4 dimension either. But for study Ricci flow, there's sort of unstable and stable ones. This is a common feature in all the geometric flows, that the unstable ones, I mean second variation unstable, you typically could, your hope can be perturbed away. And so you could, so more essential as far as the flow concern is more essential is the so-called generic singularities, which will be basically stable ones. Okay? So that's what you're going to discuss what are the possible stable ones. So in this case, there's one conjecture by Hamilton concerns particularly the four-dimensional ones. So let me mention that, and we're going to discuss some of the related results. So I'm going to erase these. Oops, sorry.
If you let G and F freely move this function, what would you say?
In this case,
Yeah, with a constraint.
well, in the sense, the thing is, F moves according to what, right? So actually, if you if our for the Ricci flow, typically, as Paraman did, is we forward the equation for that metric G, of course, say for example, right, follow the Ricci flow, and then the F turns out will be a backward one. So you say, suppose at certain later time, any later time, capital T, you start to get the backward heat equation. Yeah. You take critical points of which functional?
With a constraint.
With or without constraint?
With constraint.
This one then.
No, with just this equal to 1.
But not doing the minimizing, you mean?
Not
Okay. All right. Well, we have a string theory expert here. So the question is, what equation does F would flow meaningful? I think that itself is an interesting one. Is there any sort of course, for us, it's more study Ricci flow and hopefully understand geometry. So F is auxiliary in a sense. So the question will be, is there any physical or some interest situations that F, for example, there's a coupled one is the harmonic sort of map. There's other, so the metric flows with Ricci flow, and you also can, as the metric changes, you also flow metric, the maps or function by the heat equation. That can be done. That is started, in a sense. You can consider, say, standard d f dt is equal to Laplace, but gt here of the f, maybe. So there's a couple of equations, yeah. So it well depends on what is your interest is, right? So this extends some of the fixed metric situation to the moving metric. Okay. Okay, so let me so in around 2004, myself and Hamilton and Tom Ilmanen, we consider the second variation of the mu entropy. But for Einstein, positive. Einstein manifolds. Of course, you can also study the Ricci flat ones too, but I think today we're going to focus on Einstein manifolds. So in the sense is Ricci shrinker. Let's say compact. Okay. For simplicity, we're going to do just the compact. Okay. It is called mu entropy stable if the second variation of in sense is in the sense Ricci flow is monotone increasing, so more like you are local. If you hit local maximum, then this one should be less than equal to 0, right? For all symmetric two-tensor H. The symmetric two-tensor. So that's in the tangent space of metrics, right? So that's essentially you are more like a local maximum. All right. So here it is for general ones. Now, one of the we actually studied what kind of Einstein manifolds in some special cases. So I'm going to write down second variation formula in a minute, which will take a little bit more time. But let's just get down to what's the open problem. So the main conjecture is so Hamilton's conjecture this arrived about 2004, shortly after we wrote the paper, which is on archive, is that the only for the compact stable Einstein manifold with a positive scalar curvature around S4 in complex projective space CP2. The sphere, of course, is strictly stable, but not just the linear stable, but actually dynamic stable. It means if you perturb a metric, any perturbation of a standard random metric under the Ricci flow, then you know that they'll come back. So it's actually dynamically stable. But CP2 is sort of weakly stable. And yeah, so so this is just for after 12, yeah.
CP2 is stable if in the Taylor class, right?
Well, that's a difference. Yeah, there will be a difference we can talk about. CP2 will be strictly stable if you are deforming the Kähler category. For example, all the Kähler-Einstein ones with positive scalar curvature will be stable if you stay in Kähler category. But as soon as you are talking about remaining category, the Kähler-Einstein ones, except CPN, like CP2, a lot are not stable. For example, all the four-dimensional Kähler-Einstein ones, CP2 blob 3 to 8 points are all unstable, right? So depends on which we are to study in the remaining category of Kähler categories. Yeah. But even in the remaining case, so this is weakly stable, this is strictly stable. So 4 dimensions, that's still open after 12 years. So we still haven't been able to done that. And unlike mean curvature flow. So I'm going to mention some of the results, what's known, and I think this one similar to the in some sense like the Hitchin-Thorpe question is all comes down to understand the vowel part, or actually self-dual of the vowel part, for example. So I think we haven't found the right enough information here. So hopefully, right? Because Einstein, you don't have much information on the remaining vowel curvature parts. And and on the other hand, as we will see, if we have I erased the Laplace, the second variation will involve the Lichnowitz Laplacian, and there's a part is the full curvature tensor appears. So even if you're Einstein, you still have the vowel part appears there, and how we can sort of handle the vowel part. That I think maybe more hopeful if actually if we are on the non-trivial Ricci solitons, then we have the potential function. Then, as Jopin pointed out, like in their work with Ovidio in the 4 dimension at least, that then you can hopefully reduce the full curvature tensor maybe more to the Ricci part and go on. But anyway, so that's the question. So what is second variation formula? All right. So let's explore the second variation formula. So here's a proposition 2004, and that's is the second variation. For Einstein matrix. Okay. So now, so let M and G be Einstein with the Ricci equal to either 1/2 or so let's say 1/2 of G. Okay, so we're going to normalize to be 1/2. That's more convenient for us. So that's the positive Einstein case. Okay, and let H to be equal to delta G belong to any symmetric 2 tensor. Then the second variation so this is going to be, so tau will be 1. So and we call it the operator N acting on H, second, so it's a second order operator and d mu of G. Now, the Jacobi operator is going to be, so let me copy it down here. There's several parts. So where N of H is going to be, the first part is the Lichnowitz Laplacian. Okay. Maybe slightly, it's not quite the entire. So let me write it down as this. So Laplace of the acting on the symmetric 2 tensor plus the Riemann more as, not quite as the curvature operator, but as the bilinear form on symmetric two tensors. Okay, not on form. I'll write down in a minute. So this, you got another symmetric two tensor, plus the divergence star of divergence of H, and plus 1/2 of Hessian. And this is a little bit different from just without. So this have there's a function you have to solve equation and take the Hessian. So let me just write this part down in a minute. So this is the V is the function, and minus here is the multiple of the metric, and here is 1/2 times dimension times the volume of M, and you have the taking the trace of H integrate, and the whole thing is multiplied by the metric because everything is symmetric two tensor. So that's it, and the Laplace of VH plus 1/2 V of H is equal to double divergence of H, which is a function. So this part, in general, gives a little bit complication. All right, are there any questions? So we're going to write down in say local coordinates. So now the Riemann of H, this part is basically equal to Ri j k l, and then you got the H j of L. So if this is Ik, all right, and the divergence of H, we know that this is like the it's the H say J and Ij, all right, and divergence for any one form. So this you got one form. For any one form, omega, the divergence of star is the dual of omega now gets back to two tensor. So this is Rij will be equal to minus 1/2 di omega j by dj omega I, or if you like, this is also equal to the Lie derivative. So equal to minus 1/2 of Lie derivative of the dual vector fields, right, acting on the metric T. So that's what these notations are. So that's the full second order operator coming here. There's some similarity with the mean curvature flow case, and here they have Laplace and you have some others. So we'll see that these. Okay. So all the works have to analyze whether this quantity has a sign, right? And that, so that's all the works has to be done here. I think what time is so maybe a few more minutes. Yeah. Maybe should take a break. Any questions? Because here is just the formulas. So maybe when we come back, yes.
So in 4D, right? Because there is a nice curvature decomposition, right?
Yeah.
So is that formula will be nicer or? Doesn't help.
Well, in the sense that the only, of course, the part is, I think here. The part is for the mention, the help is that this part can be simplified, right? in a sense. We have the curvature decompositions. Yes, so that's the hope. Yeah. But still you involve the W plus and W minus, certainly, right? You have decompositions. Right? You want to explore self-dual and anti-self-dual sort of situations. Yes. But still, that part is not very well understood yet. So how do you so needs to understand. I think 4th dimension for the compact shrinkers is really try to understand the W plus W minus, how that part, except I think, if you assume some sort of harmonic, say the divergence of W plus equal to 0 or something like that. There's some results on that one. But if you do not assume any sort of the Weyl tensor has certain properties, what can you do? Yeah. Mm-hmm. But here, hopefully, is using if you say stable, then force the Weyl tensor or part of Weyl tensor to be special. That's the hope, right? Hamilton's essentially. There's the Hitchin has a well-known theorem. So here is a clue. So what is possibly we could do? So maybe I mentioned this one is maybe a pathway to link is Hitchin has a theorem. I think was late something like 98. I forgot exactly what Hitchin has theorem says. If you have if M4G is Einstein, and positive, right? So say Ricci is equal to half, say for example, half of G, and say W plus identically equal to 0, then you know that this is the case. So this is self-dual. So self-dual. Actually, Einstein, it's all other. The only thing is in this case, is S4 CP2. So one of the possibility is this is more about sign, and that's the one. So maybe we come back to discuss a little bit more of this. Yeah.
I think we have 20 minutes.
Oh, okay. Okay. All right. Yeah. Yeah. And then so I'll probably next 10 minutes, and then I'll move on to some more rigidity in the steady solitone case and discuss. So here's just a brief one. So of course, if you're interested, we can discuss more, and I listed some references there.